Resonance has wide applications in energy processing and signal processing. We will discuss several interesting examples in this lecture. You will find resonance extends the application range of dynamic circuits. We will introduce the applications in two aspects. The first is in signal processing. As we know, we can adjust the tuning knob to choose the frequency of a radio station. What's the basic principle? In the front of the radio receiver, tuning knob corresponds to a changeable capacitor. It connects to an inductor in series. This inductor is coupled with another inductor. The coupling of inductors will be introduced in the next week. It's regarded as a connection of an inductor and a capacitor now. After being coupled to the next stage, the signal is transmitted through the amplifier, the detector, and other processing circuits, and finally broadcast by the loudspeaker. But in fact, many signal voltages may be received by the receiver. For example, 3 radio station signals are detected, and their amplitudes are all 10 milliwatts. In this circuit, the inductance is constant 250 microhenry, the resistance is constant 20 ohms, and the changeable capacitance, the current value is 150 picofarad now. We can get the resonant frequency is 820 kHz. Let's focus on the characteristic of the current for 3 signals with different frequencies. All the 3 different radio station signals. Because by the coupling inductors, different currents induces different voltages on the second stage. The larger the current is, the larger the induced voltage is. We suppose that the frequency of the 3 radio stations are 820 kHz, 640 kHz, and 1026 kHz respectively. We solve the inductance reactance, the modulus of capacitive reactance, and the reactance of the whole circuit at 3 different frequencies. At 820 kHz, the circuit is in resonance, so the reactance is 0. At 640 kHz, the whole circuit represents capacitive. At 1026 kHz, the whole circuit represents inductance. The amplitude of all signal voltages are 10 milliwatts, so we can solve 3 effective values of the current for different voltage source. At 820 kHz, it equals 1 milliwatts over 20 ohms. At other frequencies, it equals 1 milliwatts over the corresponding modulus of the impedance. What's the actual meaning of these different currents? Let's look at the magnitude of the frequency characteristic of the current. At resonant frequency, the current is 0.5 milliampere. At other 2 frequencies, the current is 0.015 milliampere and 0.017 milliampere respectively. They are 3% and 3.5% of the resonant current. That means all the 3 signals with different frequencies are received by the receiver with the same amplitude. But due to the selectivity of the RLC series resonance, the current reaches its maximum value at resonant frequency. According to the definition of quality factor in lecture 74, you can find that the circuit with higher quality factor has a narrow magnitude frequency characteristic. In other words, the decay of signals with other frequency is more obvious. The second example is the application of the resonance in energy processing. Suppose the current source delivers not only the energy needed by the load, but also the energy of the harmonic waves. Do you still remember the power system in lecture 60? In HVDC, that is a high voltage direct current transmission system, it's very common on both sides of the converter station. The branch parallel to the load is designed for harmonic waves to flow through, so the harmonic waves can't flow through the load. That's realize the function of the band stop filter. Let's draw the magnitude frequency characteristic of the impedance of the branch seen from the 2 terminals. When the frequency tends to be 0, the capacitance plays the leading role. The trend of the modulus of the capacitive impedance is like this. When the frequency tends to be infinite, the inductance plays the leading role, and the magnitude frequency characteristic of the inductor is like this. In resonance, the whole circuit represents the characteristic of the resistance, and the input impedance is R. So when magnitude frequency characteristic of the impedance decrease first and increase later, and its minimum value is R. It's like this. The corresponding frequency of the minimum value is 1 over 2 pi times the square root of LC. From the characteristic, we can see that this is a band-stop filter. Next, let's do a simulation to observe the function of the band-stop filter in parallel to the load. Sometimes the band-stop filter is also called the wave trap. In this circuit, a current source provides power to the load. A band-stop filter is in parallel with the load. According to the value of L1 and C5, we can solve that the resonant frequency is 600 Hz. At 600 Hz, the impedance of the whole branch is 1 ohm. So this is a parallel connection of 1 ohm and 5 ohms. The current with a frequency of 600 Hz mainly flows through this branch. For the current with other frequency, this branch represents larger impedance, so these currents all flow through the load. This realizes a function of eliminating 600 Hz harmonic current. Let's start the simulation. We know that the resonant frequency is 600 Hz, so the frequency range is from 400 Hz to 1 kHz. The output is the current through R1 and R2, that is the filter branch current and the load branch current. Delete the phase frequency characteristic and change the range of the horizontal and vertical axis for better observation. The green curve represents the current through the filter branch. The red curve represents the current through the load. The two curves both have a peak here. In other words, the current with the frequency near here mainly flows through the filter branch, and the current with other frequency mainly flows through the load. Move the cursor. You see, the frequency is 600 Hz. The current through the load is 173 milliampere, and the current through the filter is 830 milliampere. So the 600 Hz harmonic current is almost bypassed by the wave trap.